Okay, so before we begin the lecture, a couple of announcements. So first of all, the first paper review will due tomorrow. Okay, so paper one, the unit, so it's due tomorrow. Okay, so don't forget about, forget to submit your review report. Okay, and if so, I already provide this kind of review report example. So feel free to check it out. You can follow this example to, writing your report. And the second thing is oh, by the way, so the next paper assignment is already out, right? So you can see paper 2. I also released paper 3. Okay, so if you have time, please go ahead, starting to reading the paper, prepare the report early. And second thing is the presentation selection. So I see, many of you already, go through these list of papers and, make your selection, and also the presentation date. So if you haven't done this already, please, go through the remaining, papers, right? If the paper is already claimed by someone, you cannot, pick the same paper for presentation. You have to pick some other papers. Okay, but still we have a lot of options. Please, make your, selection as soon as possible. Then, and also decide which class you want to make the presentation. So once everyone select the paper and select the date, then I can post this on the Canvas, so everyone knows the schedule. Okay, which day you will do the presentation. Okay. Okay, so for today's class, we'll talk about deep learning. So I'll provide like you can think of this as like a crash course to deep learning if you don't know anything about deep learning or machine learning in general. So this class and the next lecture will basically cover some of the fundamentals or very basic of the deep learning. So when you're reading the papers, you know some of the concept and how the deep learning works. Okay. Okay, so you may heard a lot of these buzzwords, right? Maybe the most heard one is the artificial intelligence, AI, right? So if you talk to the like a Uber driver, they know AI, right? So they want to using AI maybe to do something. Okay, so that's definitely is one very emerging area for medical image computing. A lot of AI has been used in medical image computing. So AI is a very broad area, right? So in the subfield, that is machine learning. Okay. So, and in the machine learning realm, we also have a sub field that is called deep learning. So deep learning is recent, very popular area that basically using deep neural network to do all kinds of learning tasks, right? You can apply deep learning to computer vision. You can apply deep learning to natural language processing. You can apply deep learning to, speech recognition. Of course, you can also apply deep learning to some other applications like Medicare or healthcare, right? But why we want to use deep learning? Okay, so compare with the traditional machine learning. So here is like a brief diagram show what typical machine learning or classical machine learning do. For example, you want to perform the task of image classification, right, or object recognition. So giving like image, right, this is a cat image. So the classical machine learning, well, first, what do? We want to extract some of the meaningful features, right? So the first step is feature extraction, okay? Then if we, once we have those features extracted, And then we're using, some of the classification method or some classifiers and train it to classify, what classes this image belongs to, right? Cat or maybe another class dog, right? So feature extraction actually, researchers devote a lot of time and effort, right? Trying to come up with, the discriminative features that is able to distinguish, among different classes, right? So how this feature is able to distinguish this cat image from a dog image, right? Or maybe from a bird image, right? So there's very serious, engineering on the feature, okay? But deep learning now, we want to do, feature extraction and a classification in just one go, okay? So we use a unified framework to automatically extract the features and using that to do the classification, okay? So basically we let this network to decide which feature may be the best or the optimal for the classifier to recognize this is a cat image with high confidence. Okay, so we no longer require like two separate stages, right? Do the feature engineering, then using that to train the classifier. We do these in a combined step, okay? So, so here are some of the features we can see, right? So for the network, we can learn some low-level features, right? So basically like edges, right? You can see different directions, right? Vertical, diagonal, right? So we can learn some mid-level features, right? Maybe we can detect like, if we're doing face recognition, we maybe detect like eyes, nose, ears. And we also, able to learn some high-level features, right? We are able to, learn some of the basic face structures, okay? Another question is why now, deep learning is, so popular, right? So what, give this kind of explosion of using deep learning in all, disciplines, okay? There's a couple of reasons. So one is the big data, okay? As we all know, deep learning is very data hungry, right? It's a data-driven approach, right? We are leveraging the data, trying to discover some of the patterns from the data, right? We are living in this IoT era, right? We using our cell phones, right? We share all the data on the internet, right? We have, for image, we have, Facebook, Instagram, right? We basically share our daily life images, on those very popular platform. So you get a lot of those data. And for videos, we have YouTube, right? So you basically you can find any type of videos on YouTube, right? Data is not a shortage, okay? And so that's one very big reason why this deep learning is able to take off at this era. So that's the big data. And second, we have the hardware. Okay, so process these a large amount of data requires a lot of computing, right? So before we only have CPUs, right, which is not good at processing images, and or is not able to perform fast on a large volume of data. But now we have these graphic processing unit, which is especially good at processing, image data, right? Because it's massively parallelization. And we are able to using these kind of GPU clusters or servers to train, your large models on a large amount of data. Okay, so that's the, the second reason we are able to see this kind of constant, advance of the deep learning technique. And the third is the frameworks or software, okay? Right, so we have a lot of, standard, softwares researchers or, industry practitioners can use, right? We have TensorFlow, we have PyTorch, Caffe, and other, softwares that, people use to do some development of deep learning. So TensorFlow or PyTorch are two widely used software or deep learning frameworks people are being using. Okay, and a nice thing about the software and toolbox is that a lot of functions are built in, right? So they have built-in functions. It's just a basic function call. You can load the data and pre-processing the data, right? For example, you want to do some data augmentation. There's already built-in functions can do that, right? You don't have to write the code from scratch yourself, okay? And for training the model, right, the backpropagation gradient descent algorithm is also already being built in there. So you also don't have to implement those algorithm by yourself, right? So it's basically just a function call. You are able to achieve this kind of functionality. It's very easy to use. You can quickly prototype your network. Okay, so basically you can focus your energy to kind of build your network rather than crack the very bottom, how each component has been implemented. Okay, and the fourth is the open resource, right? I'm sure all of you guys have heard about GitHub, right? So basically, researchers been posting their papers or their source code on GitHub, right? So this is trying to facilitate reproducible research, right? Because a lot of time, you don't want to reinvent the wheel, right? If you're able to share your code with the community, then people can quickly leverage your code, right? And do something and modify and maybe build upon that, right? So you don't have to, starting from scratch, follow the paper and do the re-implementation. That will take a lot of time, okay? I remember when I do the PhD, when we write a paper, we compare, with different methods, right? So I think a lot of time we'll just, spending time and effort trying to implement someone else's method, right? Because they don't share their code, right? And if the setting is different, right, I have to use their algorithm, test their algorithm on my setting, then I can do a fair comparison. So that ends up, I have to read understand their method, a little bit of detail, a lot of their small details, and trying to reproduce the result as close as possible so that I can using their method to do a fair comparison. Okay, so that actually take a lot of time. But now, if people sharing these kind of open source their method, that will save other researchers a lot of time. Okay. So just one word to describe what is machine learning is basically we are trying to looking for a function, right? Mapping your input to the desired output, right? For image recognition, we want to, the speech recognition, giving the input is a speech, right? And we wanted to convert it into a sentence on the terms, the words, right? So how are you? And for image recognition, the input obviously will be image, right? So we want to find the function that is able to map this input to a specific output, right? A category, a cat, a dog, etc. And for playing Go, right? So we want to figure out what's the next best move, right? And also for a dialogue system, right? Given user have an input, right? And we want to engage this kind of dialogue, what can be your response, right? The system response. Okay, so I'm sure you all have some sort of this kind of experience, right? One example is the chatbot, right? A lot of customer service, they provide this kind of online chat, which is basically an AI or machine learning system, a dialogue system, right? You type your question, the system is able to respond, right? If they are able to figure out the answer. If they cannot figure out the answer, then they will kind of direct you to the customer service, which is actual human being to answer your question. Okay. So what is the general framework of the machine learning? So let's use image recognition as an example, right? So I want to find machine learning model or mapping function that is able to map the input to a desired output, right? The class label. Okay, so essentially we can have a lot of functions, right? Mapping functions able to map this kind of image input to a class category, right? And so, for example, we have this F1, F2. We consider these are different functions. And for F1, give a couple of examples here. We are able to map to a class label, right? Cat and dog. And say we have another function, F2, we're also able to map the input to the labels, okay? So here I have to decide this is a monkey and decide this image is a snake, okay? So we consider all these are machine learning models, okay? Different functions, different models. And we also will require a training data, right? So for the training data, that basically is just a collection of images. And at the same time, each image will accompany with a label. So these labels can be generated by human readers, right? Using human annotation to decide what is the correct label. Okay, so we consider this is like the ground truth. Okay, so that's the correct label for these training images. Okay, and we use these training data to decide, okay, how good is this individual function, right? We have F1, F2, F3, etc. Right? So we want to decide, okay, or determine how good is this each mapping function. Okay, we're using this training data, right? For this particular example, right, here F1 is able to predict these two images correctly, right? Cat and dog, right? F2 kind of make the wrong prediction. So in this case, we consider F1 is a better model because it's able to predict more correctly on these training images. Okay. So because we supply these kind of labeled data, right? Each images we have the labels, so we kind of have the supervision, right? We have this kind of human supervisions here, right? Human labels to supervise the machine learning model. So that's what we call this supervised learning. Okay. And the process of picking the best function is the training stage. Okay, so we want to, in the training, we want to pick which function give you the best outcome. Okay, once we pick the we have identified the best function, then we can apply that to the testing stage. Okay, testing stage means you have some unknown data, right? We don't know the label of these images, but since we already identify a good, prediction or mapping function, we're going to use that to generate the prediction. We're going to trust this model prediction. Okay, so that's the training phase and the testing phase. Okay. So just to sum up, right? So for the training phase, right, we basically want to, figure out, we have a collection of functions and we use the labeled data to measure how good is each function. And we want to pick the best one during the test phase. Okay. And now let's look at, each individual step. Okay, so let's first look at, define a set of function. And we'll look at how a neural network is able to define a set of functions. Okay, so in a neural network, by name, it will compose a lot of neurons, right? So its analogy is the brain is the biological neural networks, right? So a neuron is basically a simple function, right? So you have this input, okay? And we also have the weights, right? Each input will connect with the weights. And we're basically doing some this weighted sum, right? A1 multiply with W1, right? Etc. AK, WK, we do the weighted sum. And then we add a bias, to this weighted sum, and we have this Z, which is the output, and we also have activation function, okay, and to generate the final output A. So these W, right? So we call this weight, and B is a bias. Okay, so that's the like the basic structure of the neuron, how mathematically this neuron works. Okay, weighted sum plus the bias go through activation function. Okay, and let's look at an example here. Okay, so let's maybe define a very simple one. So let's consider the bias, the scalar 1. And we also define a weights, right? So here we consider these very simple example. We only have 3 weights here, 1, -2, and -1. Okay, and we have this 3 input, right? Each connect to a weight. Okay, so the first step is doing the weighted sum, which is simple, right? To multiply 1, 2, -1 multiply with -2, we have 2, right? Some, and also 1 minus multiply with -1, we have -1. So when you sum them up, you get also plus the bias, right? We got 4, right? 2 plus 2 minus 1 plus 1, we got 4. Okay, then we take this value 4, we go through an activation function. Okay, so I'll talk about activation in a minute. We have a couple of different choices to use different activation functions. But for now, a very common one used is the sigmoid function. Okay, so there's other popular ones which we'll discuss later. So for this sigmoid function, so you can see this is a monotonic function, right? In the range of 0 and 1. Okay, so basically it kind of squeeze any of these value before the activation function to the range of 0 and 1. Okay, so for this particular example, we generate our output of this neuron is 0.98. Okay. Okay, so for a neural network, we're just not just a single neuron, right? We have a lot of neurons have different types of connections to each other. Okay, so this is mimic how the biologic neural network, as the human brain works, right? So for the human brain, the biological neural network, right, has billions of interconnections. Okay, and as the brain learns, these connections are either formed, changed, or removed. Okay, so we want to mimic this kind of biological neural network, right? So we have a lot of neurons, and we can just like you place or build like a Lego, right? How you connect different neurons, right? Different connections leads to different network architectures. Okay. And each of the neurons can have different values of weights, right? So for these 3 weights, I can have one set of values. For this neuron, these 3 weights and a bias, I can have another set of values, right? So each of the neurons can have different value of weights and the biases, okay? And the weights and the biases are considered the network parameters. Okay, so we use data to represent the network parameters. Okay, so let's look at one type of neural network, that is the fully connected feed-forward network. So here are the weights, right, of the each of the neuron connect to the input, right? The fully connected means each input will have a connection to each of the neuron, right? So we have, connection to this neuron here. For this neuron, I'll connect to this input here, and another input, right? So for this neuron, I'll also have connections to this input and another input, right? So they are all connected. Okay, so I have this weights and also have the bias, right? As you can see here, these are 2 different neurons with different parameters, right? The weights and the biases are different. And for the input 1 and -1, we can generate output of the neuron, right? So, assuming we are using the sigmoid function as the activation function, we can generate the output of this neuron, okay? Here we can generate output for this neuron as well, okay? And then, we consider this output as input to the next layers of neurons, right? These are indicated by this red color. Okay, so here this neuron has also have different set of parameters of weights and the biases. Okay, so we take the output of the previous neurons, right? So from the blue ones, the output as the input to the red neurons, and we can repeat the process, right? Weighted sum and go through the activation function, sigmoid function again, we can generate the output. Okay, so then we can move forward to the next layer and we do the same. And eventually we reach the end of the network. That's the final output of your feed-forward network. Okay. So if we change the, if we change the input, right, we eventually get a different output value, okay, assuming the neurons, the weights are fixed. If we change the input, then we get a different, output corresponding to that input. So essentially these feed-forward network is a function, right? We map input, right, one end to the output, the other end, right? So this is a mapping function. So what does this mapping function do? So this is the input, right? The previous example we look at it, right? The input vector 1 minus 1, and this is the output based on this mapping function, right? This is the another input vector 0 and 0, which is this example, and this is the corresponding output vector. Okay, and this is this mapping function gives you the output. So basically now we can say that if we, given these network parameters, right, we are able to define a function, right? If these weights are changed, right? Let's say I change this to 0, this maybe to 5, etc. Right? Any of these weights or parameter is changed, then we essentially define a different function, right? Because these weights changed can change your, eventually change your final output, right? So that consider a different mapping function, right? Okay, so, for same structure, network structure, we change the parameters, we can change the mapping function, okay? And this network structure, we can consider that it is able to define a function set, right? And if we change the parameters, that change the functions. And of course, we can build many layers of these neural, fully connect neurons, right? So we have this input layer, and we also have this output layer. Okay, so that's the, we consider that's the last layer, right? What's your desired output? So in between the input and the output layer, we consider all these layers are hidden layers, okay? They do some magic here and mapping your input to some output, okay? And, you can make it deep, right? You can, stack as many hidden layers as you want, right? 20, 30, 100, 1,000, if you want, you can build a very deep, fully connected feed-forward neural network, okay? And also in each of the hidden layer, you can also specify how many neurons you wanna use, right? So you can build like a very deep, also very wide network, right? Wide means you have a lot of neurons, right? Of each of the layer, make this network very wide. Okay, so here let's see some of the very classic convolutional neural networks. So for the the first CN, the AlexNet in 2012, which composed like 8 layers, and later 2014, the VGG network, which has 19 layers. And the same year, GoogleNet has 22 layers. Okay. And, and in 2015, a year later, the residual network, the ResNet, right, is able to have 152 layers. Okay, so make the other networks like a dwarf, right? If you do this kind of, comparison. The reason for ResNet is able to stack so many layers is because of this special structure called this skip connection, right? You have this identity mapping, so this make your network is able to learn better, training stable. You are eventually able to stack many layers to build a very deep network. So, later we'll look at the details of these different network architectures. But here, just like a side-by-side comparison in terms how, this neural network is progressed in terms of, the deepness. Okay, so another very important component is the activation function, right? We talk about in the single neuron structure, right? So we have a weighted sum plus the bias, then go through this activation function. There's a couple of common activation functions, right? So here I list 3 of them. So one is the sigmoid function, and the other is the hyperbolic tangent or tanh function, and also the rectified linear unit, so ReLU, so which is widely used in modern deep neural networks. Okay, so ReLU is mostly used. So, and actually, if you look at the ReLU, the function is very simple, right? So that is just the maximum between 0 and z. Z is your the output, the weighted sum plus your bias. That's the z, right? And you just basically compare with 0, which one is the maximum. Okay. So one thing to note is that all these activation functions are nonlinear. Okay, and if you're interested in more, activation functions, I list these kind of reference. You feel free to check it out. So a lot of researchers has been devoted to come up better activation function, to make the network learn better, generalize better, or maybe even converge faster, right? So there's a lot of very active research, but the most widely used is the ReLU activation function. Okay. As I mentioned, right, so all these activation functions are nonlinear. So the question I want to ask you is, why do you think we need to use nonlinear activation function? Anyone?
It lets you approximate non-linear functions, right?
Do you mean rather than why do we need to use it? Are you meaning to ask like why do we want to use it?
Yeah. I mean, why do we
Or
want
need.
to use? Yeah, want to use. Yeah, it's not necessary to use nonlinear. We can use linear functions, but yeah, the question is why do we want to use nonlinear activation function? Yeah, so I think one student just mentioned, right? So the want to map the nonlinear function, right? Decision boundary. So let's look at this very simple example here, right? So here we have these two-dimensional space. Okay, we have these points, right? We have 2 classes. We want to classify these 2 classes, okay, the red and the green, okay. So let's say, we use linear activation function, okay, so linear activation function will just produce, linear decision, boundary, right? No matter what the network size is. Okay, so basically you come up with this, linear decision boundary to separate these two classes. Okay, for this particular case, right, no matter how you change the slope, right? So a linear decision function is not able to perfectly separate these two classes. I mean, you could, right, if you're using some kernel method, right, to lift these 2D data into a higher dimensional space, for example, 3D space, right? Maybe one class of data like this red, right, sets higher, above these green points, right? Maybe you can using a linear hyperplane, right? Just you cut a cake, right, horizontally, you can perfectly separate these two classes. But let's just consider you are not using some of kernel method to, map the data to the high dimensional space. We are still in the same space here. A linear decision boundary is not able to perfectly separate these two classes, right? Because of this linear function. But if we introduce nonlinearity into the decision boundary, right, we are able to come up with these very complex nonlinear function. So which means this function, is able to wiggle around these points, right? Depend how complex your nonlinear function is, right? You can even make a very complex function trying to wiggle around all these points, right? And make a perfect separation of these two classes. Okay, so that's why we need some nonlinearity of your decision, functions, so that you are able to kind of, able to separate these kind of complex, data structure. Okay. So if we don't using this, we don't use the nonlinear activation function, right? We're just using the linear activation function. Although we have many, hidden layers, right? But no matter how many hidden layers you are, essentially that collapse into just a single linear layer, okay? And your model, is nothing but just a simple linear regression model, okay? The learning capacity, or, the ability to handle those complex varying data points is very limited for this simple linear regression model, okay? So here is actually a very simple example just to show, okay, why if you're just building linear, using linear activation functions on all the layers, essentially just collapse into a single layer, right? So let's just, consider this one, right? A single neuron. And here you are using the linear activation function, right? One here. Then you can expand these equations, right? And essentially what you end up with is, although you have these multiple layers with different neuron weights, right? Essentially, this is just another weights, right? And these big lump of terms, you can simplify just a single bias, right? This is basically just a single layer of the linear layer, right? Okay, so there's some of the limitations of these common activation functions, right? So first of all, let's look at the sigmoid function. Okay, so this is the how the sigmoid functions look like, right? If we plot the graph, and if we compute the derivative, which we need to compute derivative, when we do the back propagation, right? So and the gradient, right? We take derivative. This is the curve of the derivative of the sigmoid. As you can see that the gradient is very small, right? From 0 to close around like 0.2. Right, and if we have many layers, these gradient, derivative, using chain rule, you're gonna multiply them together, right? If you can think about, if you multiply like thousands of very small values together, right? You eventually, the product will be close to 0, right? The gradient will be diminished. Okay, so that is called a phenomenon called vanishing gradient. Okay, so that's a problem, right? Because eventually your network is not going to learn anything, right? You vanish to 0. There's going to be no update during this kind of training process. Okay. And this commonly used ReLU function also have this limitation, right? And if because of the simplicity of this ReLU, right, max z and 0, it also have the zero gradient, right? Like the left half of the plane is just, when you compute gradient is just 0, right? We call this, the dead gradient. One way to mitigate this issue is that maybe we don't want to like a plane 0 on this left half of the plane, right? We want to introduce some of the slope so that if you compute the derivative, calculate the gradient, you still have some, small values there, right? So that's some of the like parametric ReLU or leaky ReLU or GReLU, that's the idea, right? Basically introduce some of the slope in the left half of the plane. Okay, so you don't have zero gradient. Okay, so that's the activation function, which is important component in this deep neural network. And another component in this network is the softmax layer, which is at the output layer. Right, so for the ordinary layer, right, so we have the value go through this activation function, right? Essentially, we can generate any values, right? You see, we can have arbitrary values here, but these values may not be easy to interpret, right? What does these? Let's say if this value output is -5, this is -10, and this is 20. Right? What does these values mean, right? If you're doing image classification, how do you interpret these values as your output, right? How I'm going to use these values to make a decision, right? So in order to make it, easy to interpret or has some, meanings to make a, proper decision, we introduce this softmax layer, basically just a normalization, okay? So you're using the exponential function here, right? And we also normalize it, to between 0 and 1, right? We essentially we want these output behave like a probability, right? So probability between 0 and 1, right? And also all these output, each element will sum to equal to 1, okay? In this case, right, so if we were doing some of the classification, right, 10-way classification, right, then each of these outputs will be much easier to interpret, right? If this is a probability, right, then I'll just pick the one has the highest value, right, which means it has the highest probability your input belongs to this particular category, okay? So that's the softmax layer. Okay, so for this concrete example here, right, 3, 1, and -3, if let's say we go through the last softmax layer, we do the normalization and we generate these 3 output, right? So then you can easily determine, which class you want to pick, right? We want to pick this one. Is 0.88 has the highest probability. Okay, so we select this as your prediction for this corresponding input. Okay, so next we want to talk about the goodness of the function, right? How do we evaluate how good is your function, a particular function? Let's look at a very specific example. That is the handwriting digit recognition. Okay, so this is like a handwriting digit, right? 2. Okay, the way we do is, for the machine to examine these digit image, right? Machine will read these as a matrix, right? The matrix is composed with these, individual pixel values, right? Let's say this is a 16 by 16 image, right? If we, vectorize this image into a long vector, which has 256 elements in this vector, right? So from x1 to x256. Okay, we take that as input and we go through a machine learning model, right? Basically a mapping function. And we map that into a particular output, right? Here we want to do digit classification, right? How many digits are there? We have 10, right? From 0 to 9, okay? 0, 1, 2, 3, 4, 5, 6 to 9, okay? So, and we're using this output vector, right? From y1 to y10 to indicating this, the probability, right? Each corresponding as to a specific digit. Okay, so here we are consider this mapping function. We are using neural network as the mapping function, right? We map this input 256 dimensional vector to this output 10-dimensional vector, okay? So how do we do that? So this is basically, I just elaborated, right? So each pixel, we form this input and we generate this output vector. And this is the probability, okay? Let's just say for this particular example, this particular input image, and this is the output generate from this neural network, okay? And if we look at these probability, right, each element of this output vector, we select the largest one, the one with the largest probability value, right, which is 0.7, okay? And this corresponding to the class of digit 2. So we make a decision, this is image 2, okay? And of course, right, if we do the supervised training, we are not just using a single image, we will prepare like a set of data, right, training data, which maybe consists of hundreds or thousands of training images with their corresponding label. Okay, so here are some examples, right? This is the input digit image, how they look like, and this is the corresponding label for a particular digit image. Okay. And we are giving a network architecture and and a set of parameters. Okay, and we want to learn that. So this is the output, right? The output vector for this particular input. And for the training, we know the training label, right? That's our target label. So here, there's a concept called one-hot encoding, which means, we're just using one to indicating the class, that your input is correspond to, right? The other classes will have the probability of 0, okay? And now the goal is you want to, make your prediction as close as possible to this target, right? So you want your model to able to predict as correctly as possible, right? And obviously in the beginning of your model, if all these parameters are randomly initialized, your network is not going to do a very good job, right? Likely this prediction will be very noisy, right? And we are going to introduce some of the loss functions to measure, how good is your prediction, right? So we can using this kind of squared arrow, right? You just compute these squared arrows between your prediction and this target, one-hot encoding, or we can using cross entropy, which is also, like a standard loss function that's being used in deep neural network, which we'll discuss in the next lecture. But for now, we'll just know there's a loss function to measure how close your prediction as compared to the ground truth label. Okay. And ideally, if you're able to pick a good function, so your prediction should be as close to the ground truth, right? The target. So your loss will be as small as possible, right? And if we prepare all the training data, right, let's say we have hundreds, thousands of these data, and we generate we go through this network, we generate a prediction, and we measure the loss, right, for each individual training data, right? For this training data 5, we can measure the the loss for this example, right? For another image, input 0 here, we can measure another loss, right? So we can measure a total of loss, right? Let's say here we have R sample right here, right? So we can sum them up together, right? This is the total loss for my entire training data set, okay? And the goal is to make the total training loss as small as possible, right? You want to find a model that make less error, right? So that's the goal, right? Find a function in this function set that minimize that total loss L, okay? And because we mentioned that the network parameter is able to define different functions in that function set, right? So this boils down to find that the optimal network parameters theta here that is able to minimize the total loss, right? So you want to find the optimal parameter that is defining this neural network or mapping function such that it minimizes your total loss given these the training data set it is provided. Okay, so that's the idea how we want to use supervised learning technique to find the best function. Then you can use that for the testing or inference. Okay, so that's the step 3. Okay, once we use the training data set to identify that best function, then we'll use that to do the testing or do the inference. Okay. Okay, so that's a very brief introduction. Give you some of the fundamentals or basics of the deep neural network. Next, we'll introduce one class of neural network that is widely used for image processing and computer vision, right? Because this course, medical image computing, the target is image, right? We are mostly dealing with images, and let's see how convolutional neural network, works, and when they process, images. Before we talk about, the components of the convolutional neural networks or CNN, we first want to give some intuition, right? Why do we want to use convolutional neural network to process images, right? What kind of unique characteristics of images that makes us want to build this kind of, neural network, right? So let's look at this particular example here. This is a bird image, right? And, for a human, for us, we want to make a decision. This is a bird image, right? So what is the most important patterns or maybe the regions you want to look at, right? So maybe you are looking at, these, the beak of a bird, right? So that's a very distinctive features of bird, right? And maybe some of the head regions, right? So if I'm only giving you these small regions, you are able to make a decision. Okay, this object appear in this image most likely is going to be a bird, right? So that's we call the salient region. Okay, right. So that means some of the patterns or important patterns are actually much smaller than the whole image, right? So for this whole image, if you look at the background does not give you any important information, right? Or if I just select a very small region on the back of this bird, right? All you can tell is just a small fur. Maybe I'm still not able to distinguish that. But if you select these small, the leg here, you may also able to determine this is a bird, right? So some of the important patterns are actually much smaller than the whole image, okay? That means a neuron doesn't have to see the whole image to discover the pattern and make a decision, right? Remember how the fully connected neural net works, right? Remember we look at the digit image, that is we flatten those 16 by 16 image into a giant or long vector, right? 256 dimensional vector, right? So here we can also make it like a lone vector, but a neuron doesn't have to look all these pixels, right, to see all the whole images, right? We basically can look at these small regions, we can discover the pattern, which may be useful or helpful to make a decision, okay? So that means we can, design a network that connecting to a small region. That means we can use less parameters, okay? Maybe like a beak detector, right? We'll just detect the beak, then we're able to make the, discover that pattern and make a decision. And another interesting is that, the same patterns appear in different regions, right? So let's look at these two images, right? Each of them will contain a bird, right? If we are aiming, to, detect this kind of beak of the bird, right? The pattern. So maybe you have a neuron that is responsible to detect like an upper left beak, right? Detecting this position. And maybe you have another different neuron to, detect like a middle beak, right? So located in the middle of this image, right? But do we really need, these two different neurons, right? Two different neurons means their weights and the bias are going to be different, right? They have two different sets of parameters. But do we really need to have these two sets of different neurons or parameters to detect these beak? Is not necessary, right? Because they are almost doing the same thing, it's just the location is different, right? So that means maybe we can just using the same neuron, right? Using the same set of parameters, right? And maybe sliding around this image so that, the same pattern can be discovered, rather just come up with a different neuron than just, detecting a slightly shifted position, right? And then the third property is that, subsampling the pixels will not change the object, right? So if this is a bird image, if we subsample this image, right, basically like we, we select like the column 1, 3, 5, every two columns, right? For the row, we do the same. Every two columns we select, and we are able to reduce the spatial size, right? Reduce by half, maybe. We can even reduce by a quarter, right? But for this reduced image, as you can see that the object is still there, right? The position, the location, some of the characteristics of the object are still there, right? The color, the shape doesn't change, right? So that means we can subsample the pixels to make the image smaller. That implies we can use less parameters of the network to process image, right? Remember, like if we're using the fully connected layer, right? We flatten all these pixels into a giant or long vector, right? If we are able to reduce the image size, the dimensionality of that vector is also going to be reduced, right? Then the neuron connect to that input, the weight's going to be reduced as well, right? So the less parameters. So that's basically like three very nice properties here, right? So some patterns are much smaller than the whole image, right? The same patterns appear in different regions, and some subsampling the pixels will not change the object, right? We can take these properties and use that to design a specific component of the convolutional neural network, and later we'll see how. Okay, so these are the three properties we just talked about, right? So for property 1 and 2, we design these convolutional operation, okay? And for the property 3, we design these pooling operation. So here, mostly use max pooling, and we'll talk about that in detail later. And there's maybe some other pooling strategies like average pooling, right? So basically this pooling will just reduce the image size or feature map size to make it smaller, so that later layer, can have less parameters. Your entire network can have less parameters. Okay. And of course, these building blocks or layers can repeat many times, right? Because we have this notion of deep neural networks, right? You can stack these layers many times to make it deep. Okay, so let's look at how each individual operation works. So first is the convolution. Okay, we'll use a very simple example here, which is 6 by 6, right? And we have these filters or kernels. Okay, so these are set of network parameters. Okay. So basically, this is like 3 by 3 matrix. And these are the parameters of the network to be learned, okay? And each filter detects a smaller patch, 3 by 3 region, okay? And let's see how convolution works, right? So we have the image, then we lay this individual filter on top of this image, right? The top left. And then we'll do the element-wise multiplication, okay? So the element-wise multiplication, basically you just, you have 3 by 3 matrix, right? 9 element, right? Each element you multiply with the corresponding element here in the filter or kernel, right? 1 multiply with 1. So here, there's a couple of 0 there. We don't have to worry about that because multiply with 0 is going to be 0. When you do this kind of element-wise multiplication and you sum them together, you get a value output, which is 3, right? And you can think of this as like a dot product. If you vectorize them, it's basically a dot product, okay? And if we take the stride equals to 1, right? We shift 1 column. If we move downwards, which means we shift 1 row, and we moving these kernel to another position, right? We are able to get another value, right? If we do this kind of dot product here, we get another value. Okay, you can repeat the process, right? And if we decide to using stride 2, which means, okay, the initial position is here, the next position, I'm gonna move 2, right? 1, 2, I'm gonna next window up place here, which is here, right? So you can get another value, okay? So this determines how you are going to shift your window or kernel on top of this image, okay? Let's just consider stride equals to 1, and we move this window around this image from left to right, up to bottom, right? We can generate each position, we are able to generate a scalar output, right? And this is the last position of this kernel, right? We generate a value -1 here. And if you pay attention to these filter or kernels, okay, so it has this kind of diagonal pattern, which is 1, 1, 1, okay, here, right? Because we're doing this kind of element-wise multiplication, right? If any of this kind of pattern here, the same or similar as the kernel, we basically enhance, we get a very large response, right? So the first one, if you place the filter here, we are able to generate a large response in this position, right? Which is again a very large value output 3, right? Other positions, we are not able to find this kind of patterns, right? We get a very low value. So, if you look at, right? So for this particular example, for this particular filter here, you are able to detect these diagonal pattern, right? So that's the property 2, right? That it means some of the patterns appear in many places of the image, right? Here, we are able to detect these 2 local patterns, right? Diagonal edge. So you can think of this as like edge detector, right? Detect these kind of diagonal edge with this direction. And we can have another filter, right? Maybe this doing something different, right? For this case, we are not detecting the diagonal edge, right? We detecting this vertical, right? We have this 1, 1, 1 here. We have this vertical detecting this vertical edge, okay? So we repeat the process just like before, right? We generate another output matrix. We call this feature map. Okay, so this green one, right? We generate another feature map. And if we look closely, right, so the large response corresponding here, right, because this is like have the same pattern as the filter, right? We are able to detect these vertical edge for this particular image at this position, right? We get a large response here. Okay, so that's another feature map we are generating. If you have another filter 3 or 4, etc., then you can generate more feature maps. Okay. One thing you can notice that is the output feature map is reduced, right? Input is 6 by 6. Now we have 4 by 4. Okay. And this is just animation, give you more kind of visual aid how these matrix multiplication is done, right? For this kernel or filter sliding around a particular image. Okay. And if we want to generate the output have the same size, we can use a technique called zero padding, right? Basically, you can pad the zeros at the border, right? So that you can shift here another position here. You are able to generate the same feature map as your input image size. Okay, we can do the zero padding. Okay, so that one is very simple, right? So we have like two 2D image, right? Like only a single channel, right? Like a grayscale image. Typically, the natural image we are dealing with has 3 different color channels, right? RGB, red, green, and blue. So correspondingly, we'll have. So if we interpret like here is just like a giant matrix has 3 different channels, right? RGB, and correspondingly for the filter, we'll also have 3 channels so that you are able to operate in these different channel dimensions, right? So now we have 3 by 3 spatial size, and also we have 3 channels for this filter, right? And the operations, doing the element-wise multiplication and sum them together is going to be the same. Okay, so this is a very nice animation, for this kind of multi-channel input and the kernel, how filters, how you're going to process that, right, to generate the output. Okay. Okay. So just to summarize, we talk about like how the convolution is work, and we have to figure out, right, what's the dimension, for the input and the kernel size and your output, right? So let's say here my input is 32 by 32 image, right? Color image has 3 channels. Okay, use 3 to indicating 3 channels. And if I want to use a filter, I also have a 3-dimensional filter, right? The spatial size 5 by 3, 5 by 5. I also have a channel dimension, which is 3, right? So then I can operate on these 3-channel input. Okay, if I use 6 of these filters or kernels, right? Remember the example we have, right? Each filter will produce a feature map, right? So here we are using 6 different filters or kernels, then we'll produce 6 feature map, right? And if we don't use padding, right, we have a reduced feature map, right? So we end up with 28 by 28 and a 6, 6 corresponding to the channel, right? Because we have 6 filters, right? Generate 6 feature maps, right? And also depending on the stride, you also end up with different spatial size, okay? And now the next layer, right? I also use, we have to specify the filter size right now because the input has 6 channels, right? My kernel or filters will also has the corresponding channel size 6. If I using 16 of these filters, then I end up with generate 16 feature map, right? Then, the spatial size is further reduced, 24 by 24, okay? So that's how you can, stack different layers during the convolution, generate different feature maps, right? Essentially, you process these information to generate different feature representations at different layers, okay? So this is very nice, graphical illustration, right? So how this particular filter kernel, right, like edge detector, right, slice across this input, right, generate this feature map, right? Any of the position has the same patterns as your kernels, right? You get a high response, right? You may be detecting these, left diagonal or maybe right diagonal of the edge, right? So that you will generate those high response on this feature map. Okay. And this is some of the example visualize how is your learned filters or kernel look like. Okay, so in the beginning of the layer, right, layer 1 or 2, right, so usually these filters act like those very basic edge or corner detector, right? You detect those vertical, diagonal, horizontal edges, right, or maybe distinguish different colors, right? So that's the very fundamental or basic, right? When you go higher layers, right, you starting to see some very complicated patterns, right? Layer 2, you see, a combination of something you can detect. Maybe this is like a circle, right? So you detect this rectangle, this kind of shape, right? And go even higher layer, like layer 3, you are able to detect some of the structures, right? This is detecting like a human, and this may be detecting like a car wheel, right? This is maybe detecting some of the animal shape. Okay, so you can see gradually you have those high level representations of the feature. Okay. So let's make a comparison with the convolution, versus the fully connected layer, right? So this is the fully connected layer, how it works, right? So you have this input image, right? You flatten this image into a large vector, 6 by 6. You have 36 element, right? You basically have a large vector. Then each one neuron will connecting to these 36 elements of your input. Okay, but how this convolution works, right? So 6 by 6 image, right? Filter 3 by 3, and we generate a feature map, right? So let's look at the filter in the first position, okay, left or right corner, generate output 3. So if we flat this 6 by 6 image into a giant vector, right? So the vectorization here is like in the horizontal decomposition, right? 1, 2, 3. This is 7, right? Here. And the third row begins with 13, right? Position here. So I, kind of flatten them in this kind of orientation, okay? And I using different colors, right, to indicating different weights, right, position. So you can see how the output, right, is connecting to which element of your input, right? So the output is connecting only 9 of these input, right, at these positions, okay? So that means we only, we have less parameters, right? Compared to these fully connected, right? This neuron will be connecting all these 36 input, right, nodes, right? But for the convolution, this neuron only connect to 9, right? So that's less parameter. And because the convolution, the same filter will slide across the image, right? The same set of parameter, same filter slide across this image. In the next position, we get another output, right? So these connecting to these 9 input, okay? And because, they share the weights, right? I didn't change the weights, right? That means we have less parameter, right? Compared to fully connected, if I have another neuron, right, I'm going to connect this one with all these input, right? But the weights also change, right? The color will be changed, right? Not these 9 different colors. Maybe have another set of 9 different colors, right? So in this case, right, so the local processing of the convolution make less parameter. The shared weights property make the overall parameter even less, right? So that's one significant advantage of convolutional neural network as compared to fully connected layer. Okay. Okay, so yeah, so that's all for it today. We have some basic, introduction of the fundamentals of the deep neural network and also the convolutional neural network. But for the next lecture, we'll dive some details into the CNN and how the optimization process is achieved. Okay, I also list a couple of very good resources. You can look at these resources if you want to know some very basic into deep learning on different network architectures and the mechanism of how the deep learning optimization works. So these are some of the reference I encourage you to look into. Okay. See. Yeah, so we're looking more into the pooling. Okay, so the pooling is basically you can reduce the feature map size, right? So you have less parameters, to process, right? Another reason using pooling is, corresponding to the receptive field size, right? Because the kernel in our example, like say 3x3, right? You're always looking at that 3x3 region. But if you think about like pooling, you reduce the size by half, right? If I'm still looking at those 3x3 pixels, essentially I'm looking at a wider range, right? Because my image becomes smaller. The 3x3 scope, the region in that reduced sized image is actually looking at more context, right? As compared to the initial size. So that's another advantage of using the pooling, trying to reduce size, in a way is trying to increase the size of the receptive field. Okay. Okay. All right. So yeah, thank you guys. I'll meet again on Thursday. Okay.